Well, good morning, Amherst. Welcome to the continuing saga of COVID-19. Tungsten, you gonna come on the video today? He's been out and about in the rain. He's quite the spelunker. Did you know that male turkeys, toms, they will gobble in response to things like crows? Sometimes you can get them to gobble. Sometimes at the end of the day, you can owl hoot at them and they'll gobble back as well. Now, I am no owl caller, but it goes something like this. Who cooks for you? Haven't had much luck with those two calls, but hey, you never know. I'm hopeful. All right, down to brass tacks. You're going to need your calculator today. We're going to put you through your paces on that one. So we're going to talk about pH. And P, by the way, these are notes, and I've got about 16 pages of them here, so that's going to be a big one. P is for power. The P in pH, that's for power of 10. It's a logarithmic scale, much like the Richter scale from earth science. So pH is defined as the negative log of the hydrogen ion concentration in a solution. And in this unit, hydrogen ions and hydronium ions are interchangeable. So it's the negative log of the hydrogen ion concentration or the negative log of the hydronium ion concentration. That's the mathematical definition of pH. Now, logarithms base 10 are a little bit interesting things. So 10 to the 0 power we know is 1. Well, the log of 10 to the 0 power is 0. The log of 1 is 0. 10 to the first power is 10. The log of 10 to the first is 1. Notice it's the power. 10 to the second power is 100. Log of 10 to the second power is 2. 10 to the third power, log of 10 to the third is 3. Get it? Okay. Well, if I had small numbers in between 0 and 1, like 1/10, it's 0.1, that's 10 to the minus 1. And the log of 10 to the minus 1 is negative 1. 1/100th is 0.01, 10 to the minus 2. The log of that is negative 2. 1/1000th is 10 to the minus 3. The log of that is negative 3, etc., etc., etc. Well, scientists don't like to talk in negative numbers. So if you take the negative of a negative, for example, the negative log of 10 to the minus negative 1 is the negative of negative 1 is 1. You'd say, oh, the pH is 1. So that's all they're doing. When they say the negative log, they're just using a negative to negate a previous negative. You're talking about concentrations which are going to be in molarities which are pretty low, numbers that are in between 0 and 1. Excuse me. Okay, so when you look at the pH scale, it's based on a 14-point scale. You ever wonder why that is? No, we're going to explain that today. But we know from previous stuff that in between 0 and up to 7, that's acidic, and in between 7 and 14, that's basic or alkaline, and 7 is actually neutral. So we know from our previous lessons that the hydrogen ion or the hydronium ion is the acid part. So in acidic solutions, you have more acid than base, more hydrogen than hydroxide. You have a higher concentration of H positive than OH minus. And in a basic solution, it's the exact opposite. Try and get that on the screen. You have more hydroxide than hydrogen. You can, of course, say less hydrogen than hydroxide. But when they are equal to each other, you have a neutral solution of pH 7. So since each number on the scale represents a power of 10, an order of magnitude, if you will, the concentration change is tenfold with each whole number. 10 times. So a change from, say, 2 to 3, that's a 10 times change in the relative acidity or alkalinity. So a solution of pH 2 is 10 times more acidic than a solution of pH 3. The hydrogen ion concentration is 10 times higher in pH 2. You could say the hydronium ion concentration in a solution of pH 2 is 10 times higher than the hydronium ion concentration in a solution of pH 3. It sounds pretty fancy. Or you could say the hydroxide ion concentration in a solution of pH 2 is 10 times lower than the hydroxide ion concentration in a solution of pH 3. You're just looking at it from the base perspective. They're tied together. Acid, base, you know. If you know one, you actually know the other. We'll get into that. So what if you had something like pH 2 versus pH 5? You know pH 2 is more acidic, but how much more acidic is pH 2 compared to pH 5? Well, 5 minus 2 is 3. Is it 3 times more acidic? I don't think so. These are powers of 10, so is it 30 times more acidic? No, I don't think so. These are powers of 10, so it's 10 to the third times more acidic. 10 times 10 times 10, it's 1,000 times more acidic. pH 2 is 10 to the third power, or 1,000 times more acidic than pH 5. The hydronium ion concentration in a solution of pH 2 is 1,000 times higher than the hydronium ion concentration of a solution of pH 5. Those are typical Regents questions. What is pH based on? Well, it's based on the auto-ionization of water. Self-ionization. To a small but measurable extent, water breaks apart. It ionizes in water. Water in water, some of those molecules are going to break apart. So in Arrhenius theory, we might say liquid water to a small forward, mostly backward degree breaks apart into hydrogen ions and hydroxide ions. In Bronsted-Lowry theory, you'd say, well, water interacts with water, liquid water interacts with liquid water, exchanges a proton to form hydronium aqueous and hydroxide aqueous. Okay, those are just the two theories we talked about yesterday. But at 1 atmosphere and 298 K, the equilibrium can be measured, and KEQ for that equilibrium, we're going to call it KW, can be determined. So if I find my supplemental reference table, if I look up here, the top one, here's the top one's Arrhenius theory. They tell you KW is 1.0 times 10 to the minus 14. The second one, here's Bronsted-Lowry theory. KW is still 1 times 10 to the minus 14. That's a measured value. That's how you get a 14-point scale on pH. So in Arrhenius theory, you'd say, all right, well, KW, it's products over reactants, this times this over that, but that's liquid, so it drops out of the equation. So it's just hydrogen ion concentration times hydroxide ion concentration. And in Bronsted-Lowry theory, it's the same kind of deal. Products times product over reactant times reactant. This is two H2Os, but they're liquid, so they're going to drop out as well. You can't express the concentration of a pure liquid. So it's hydronium times hydroxide. Either way, KW is this one times that one, the acid part times the base part. And that measured out turns out to be, at 25 degrees Celsius in 1 atmosphere, 1.0 times 10 to the minus 14. So in pure water, a small number of the molecules become ions. They break apart, they auto-ionize. HOH breaks apart, if you will. And you've got a 1-to-1 stoic between the hydrogen and the hydroxide. So for every one water molecule that breaks apart, you get one hydrogen and one hydroxide. We'll just work in Arrhenius theory. If this is X, it's X, and it's X, because it's 1-to-1-to-1 stoic. So KW is H positive times OH minus, it's 1 times 10 to the minus 14. Well, it's X times X is 1 times 10 to the minus 14. So X squared is 1 times 10 to the minus 14. Take the square root of that. X is 1 times 10 to the minus 7. X is the hydrogen ion concentration, is the hydroxide ion concentration. They're both 1 times 10 to the minus 7. So if I take the negative log, pure water at 25 degrees C, hydrogen ion concentration equals the hydronium ion concentration, which equals the hydroxide ion concentration. If I take the negative log of that, it's negative 7. Pure water has a pH of 7. That's where that comes from. It's just a mathematical representation. You say, well, pH is neutral at 7. That's because a small but measurable number of water molecules break apart by themselves, and at standard conditions, that number, that KEQ, turns out to be 1 times 10 to the minus 14, and it's a 1-to-1 stoic between hydrogen and hydroxide, so they're both 1 times 10 to the minus 7, so you could take the pH and you call that 7. Well, if you could take pH, you can also take POH. Nobody ever talks about POH, but it's the same exact deal. It's the negative log of the hydroxide ion concentration. So if this one is 7, this one is also 7. They're the same concentration. So the pH and the POH are both 7 in pure water, and they add up to 14. So in pure water, both pH and POH are 7, and because these are derivatives of the concentrations just expressed logarithmically, the hydrogen ion concentration is the same thing as the hydronium ion concentration. That's 1 times 10 to the minus 7. And the hydroxide ion concentration is also 1 times 10 to the minus 7. However, in any sample that contains water, an aqueous solution, as long as you don't change the temperature and the pressure, you're not changing KEQ, you're not changing KW, pH and POH always add up to 14. And the hydrogen ion, or the hydronium ion concentration, times the hydroxide always multiply out to 1 times 10 to the minus 14. This is always true. This is any solution. as long as you don't change the temperature and the pressure, as long as you don't change the temperature. So in an acidic sample, you've got more hydrogen than hydroxide. In an alkaline or basic sample, you've got more hydroxide than hydrogen. But they're always going to multiply out to 1 times 10 to the minus 14, and the pH and the pOH are always going to add up to 14. That's true all the time. So if you know one, you know them all. You can think of it as a box. If you know pH, you know pOH. If you know pH, you know hydrogen. And if you know hydrogen, you know hydroxide. If you know one of these corners, you know all four, because pH and pOH always add up to 14. You can always do the inverse log and come down this way to get that. And you can do the inverse log and come down this way to get that. Or you can just say, hey, these multiply out to 1 times 10 to the minus 14. So we've got a little bit of math to do here. I know I'm talking fast, but I don't want to make this a 35-minute video. So if you know one of them, you actually know all four. So let's do an example. All right? Let's say you're given pH is 4. This one. This is 4. Excuse me. 4 plus what add up to 14? Well, 4 plus 10. Not so hard there. How do I get here? Well, there are a couple different ways to do it. You could say, well, the power is 4, but this was negative. So if this is 4, this is going to be 1 times 10 to the negative 4. If this is 10, this is 1 times 10 to the negative 10. Don't forget to put the negative in there. That isn't so hard. Now, you can use an inverse log, but we'll talk more about that as we get into a more mathematically challenging example. But if you know one, hey, 4 plus 10 gives me 14. If this is 4, this is 1 times 10 to the minus 4. If this is 10, this is 1 times 10 to the minus 10. Easy peasy, not hard stuff. Same kind of deal. Second example, what if they're not whole numbers? Let's say you've measured the hydroxide ion concentration in a sample, and it turns out to be 1.25 times 10 to the minus 6. Okay. What's the pH, what's the pOH, and what's the hydrogen ion concentration? Well, you've got 4 ways to work around. You're starting, it turns out, down here. Now I can go this way, I can go that way. When I'm here, I can go this way. When I'm here, I can go that way. There are lots of different ways to go about it. I'll show you a couple different ways, okay? You've got options. That's a good thing. So we know that those two numbers always multiply out to 1 times 10 to the minus 14, and I know the hydroxide, so I can divide out, and I could say then the hydrogen ion is 8.00 times 10 to the minus 9. That's just plugging and chugging in the old calculator. So if I take the log of 8.00 times 10 to the minus 9 and then make it negative, the negative of a negative is about 8.10. I can get the pH. Now leave that string in your calculator. I'm just going to do that on your calculator so you can see this. So if I go 8.00 second EE negative 9, right? Enter. I'm going to go, I want the log of that, so I'm going to go log second answer, enter. And I'm just going to ignore that negative sign. You can see it's 8.096910013 times 10 to the 00, so that times 10 doesn't really matter. I'm just in scientific mode. So ignore the negative, your pH is about 8.10. I know that plus pOH add up to 14. So I'm just going to go, oh, it's already negative, just go plus 14. I don't care about the 10 to the 00 power. So the pOH is roughly 5.90, but once again, leave that string in there. It's going to help you. So I went around the horn in that case. I said, all right, well, I was here. I used my math here to get this one, and then I used my log to get this one, and then I added up to 14 to get this one. So in the example I just did, I went from here to here to here to here, and I got them all. But that's not the only way you can go. So let's work the same problem, and we'll work it the other way around. So now, instead of working like I did in the green, I'm going to go from OH to pOH to pH to hydrogen. So my OH concentration was 1.25 times 10 to the minus 6. So the pOH is the negative log of 1.25 times 10 to the minus 6. So if I go log 1.25 second EE negative 6, close parentheses, enter, there's my negative 5.903 yada yada yada. Take the negative of the negative, the POH is roughly 5.90. Okay, leave the string in there. It's already negative, so add 14. Oh, look it, I'm back to my pH, roughly 8.0969, yada yada, but roughly 8.10. Leave that string in your calculator. Now, here's where people tend to go wrong. You want to probably review this once or twice, but the pH is the negative log of the hydrogen ion concentration. So let's put the negative on the other side. Say, if I divided each by -1, negative 8.09 yada 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 would be the log of that hydrogen ion concentration. And don't forget to make it negative. So take this number and then do the inverse log, the 10 to the x key. So I'm going to go, oh, okay, here's my calculator. I hope you can see that. Times -1, enter. So now in my calculator, I've got the negative 8.09 number. Okay, I want to do the inverse log of that. That's the second log. It's the 10 to the x. I'm going to go second log, second answer, enter. 8.00 times 10 to the -9 takes me back to this number. So whichever way you do it is up to you. Okay, and you can mix and match and take combinations of this, but they're both going to give you the same answer, and you'll know that when you're done, if you add the pH and the POH, you're going to get 14. And if you take your two numbers that you determined for your hydrogen ion concentration and your hydroxide ion concentration, and if you multiply these numbers together, you should get 1 times 10 to the -14. You'll know you got the problem right. So if I take 8.00 second EE -9 times 1.25 second EE -6, I get 1 times 10 to the -14. So you're going to know if you got them right. It's just a matter of making la machine work for you. Homework. Some of these problems are easy. Some of these problems require that log and inverse log and how you go about it. It takes a little practice. I've seen people do these, and some people take to it like fish to water, and some people struggle with this until they figure out, oh, it's just a matter of which buttons to hit. So we're going to go on to worksheet 5. We've got some simple ones where they're whole numbers. We've got some ones that are not whole numbers. We've got some that are, that's basically simple, right? That just put it into scientific, that's basically simple. And then we've got some definition stuff that you'll find in this lesson. And I'll give you a hint on numbers 9